Then I will continue the review on experimental searches for neutrinoless double beta decay, in particular focusing on tellurium 130. So this is a short outline of the talk. So why tellurium? Why there are many searches on them, and then the experimental approaches, in particular focusing on the ongoing or under preparation experiments or R&D, and finally some conclusions. Let me start from the usual sensitivity master formula. This is a very naive formula which was already pointed out in previous talks, but it has a very important message to send. This formula outlines what are the most relevant parameters of these experiments, in particular large masses, long measure time, a low background, a good energy resolution, and of course also a good isotopic abundance, which is one of the most debated subjects for the future because it is usually most expensive. Then another point that I would like to mention is that usually there is a discussion on the so-called zero background condition. This is not actually a zero background. There is no experiment with zero background. This means simply that the number of counts during the measuring time is less than 1. Okay, and this is the translation of zero background. No counts during your measurement. And this is very important because the sensitivity in this case scales linearly with time instead with the square root of the time. And this is, from an experimental point of view, very important. How this translates to tellurium? This translates in different ways. First of all, the properties of tellurium. It has an incredible large isotopic abundance. It is actually an exception with respect to the behavior of the other isotopes, and it has also a reasonable Q value, transition energy. This is not the best one that we can have since this is below the 2.6 MeV line of thallium, but it is in any case in a good region in the multi-compton of that line. This means that there are better isotopes. They are those indicated in this part of this plot, but tellurium is a good candidate. Let me also remind that tellurium has different isotopes. In particular, we are focusing on tellurium 130 because of these peculiarities, but there is also 120, which is a double beta plus or electron capture decaying nucleus, and tellurium 128. One of the ongoing discussion was if there is a golden isotope. I do not know if we have now a final answer from theorists. This is the master formula for the transition rate, let me say. It is dominated by the phase space, then the transition matrix, and of course the neutrino mass. So some time ago there was an observation, phenomenological observation of the fact that this product, let me say, of the phase space and the nuclear matrix somehow shows an anticorrelation. Is not working in the microphone? Okay. So this means that actually we do not have a golden isotope, and all the isotopes are practically equally good. And so from the point of view of the theorists, we do not have an indication for a particular nucleus, and so tellurium is a good candidate. This, of course, is within a factor 2 of 3, which probably is not important for theorists, but for an experimental is very important. So it, in any case, important to understand what is the difference within this factor, within the different isotopes. Let me come now to the experimental approach. Historically, we have two kinds of approaches. One is the homogeneous, introduced by Fiorini in the 60s. By the way, 60s means 50 years of research on neutrinoless double beta decay. And the other is the inhomogeneous, which was introduced before, but has now been, let me say, somehow not abandoned because there are still experiments on this, but is less, okay, I do not find the word. It's less used. So the homogeneous calorimeters means the detector acts at the same time as the source of the decay. This is the most used approach in these days, and for what concerns tellurium, we have three main approaches. One is the bolometric one with Quora and Cupid. Then there is the scintillation-loaded experiment, which is SNOPLAS, and then the semiconductors, Cobra, which is using a semiconductor. As I mentioned before, there is only one experiment based on the external source detectors in which The source is observed by external detectors, which is NEMO 3. The following experiment, which is Super NEMO, is not contemplating now the use of tellurium as one of the isotopes under observation. This is a summarizing table with the different techniques, which I already mentioned, the energy resolution, which is a crucial parameter in the master formula. And it is especially crucial for the contribution coming from the 2 neutrino, which is an irreducible contribution to the background. Then the status of construction, so Quora has just started, so I can say it's running. There are 2 R&Ds, and SNOPLAS is close to the end of the construction. The laboratories are mainly LNGS, and apart from SNOPLAS, which is hosted at the SNOLab. As mentioned yesterday by George, one important thing is to have more information at the same time. So Quora is limited by this fact, it's just using for heat, it's just looking for heat, but all the other are mixing more information, and this is a very strong tool to fight against background. Let me also remind the younger people that there was a long history of tellurium. In particular, it was one of the most studied from the geochemical point of view, and there was a long-standing debate between the Missouri and the Heidelberg group on the study of this isotope with geochemical experiments. Now they have been abandoned, but it's important to remember that they were one of the approaches. So let me come to Quora. There was already a talk yesterday by Chiara on Quora, so many things have already been outlined. This is a big detector of 1 ton size, let me say. Actually, they are more than 700 kilograms, and they are organized in about 1,000 crystal of 5 centimeter side. The design parameters are a good, let me say, a good background index, which is of the order of 10 to the minus 2 counts per keV per kilogram per year, and a good energy resolution of the order of 5 keV. With these parameters, the expected sensitivity in 5 years is of the order of 10 to the 26 years. It is hosted, as I mentioned, to LNGS. The properties of LNGS have been reminded many times, so I will skip very quickly this slide. Okay, Quora is actually a technological challenge. I mean, the heart of Quora is a big, huge cryostat which hosts the detector and has to cool down the detector at temperatures of the order of 10 milli-K, together with a lot of other ancillary subsystems. So it is endowed with 5 powerful pulse tubes and a dilution refrigerator, which are able to guarantee this. Let me remind to you that also the internal part of the cryostat holds a Roman lead, a very heavy Roman lead, ancient Roman lead shield, which repairs the counter from the radioactivity of the cryostat. The construction of Quora was completed in 2016. These are pictures of the installation of the detector. I have others later. So most of the year was devoted to the installation of the detector and of the interfaces with the cryostat until in December we were ready for the cool down. These are the other pictures from the installation, which was carried out, of course, in a very protected environment. This was the first time the towers was exposed to air, so we had to prepare a special radon-free air. And let me spend some words about the technological challenge, because of course this was one of the open questions on the possibility to go ahead with the program of bolometers. Actually, building a cryostat able to cool down the system to temperatures of the order of 10 milli-K was an open question. We were able to demonstrate that this is possible. Actually, we reached a temperature with the system at full load lower than 7 milli-K, and this is actually a great success. This is the last phase of the detector. This is actually technical, so I do not want to discuss, just to show that we went from 10 Kelvin degree to base temperature, so less than 10 milli-K in about 3 days. This thanks to the powerful dilution refrigerator, which was designed by Leiden Cryogenics and demonstrated to be more performing than expected. Also concerning the stability of the system is very stable, more stable than previous cryostats. This is a 10 days period and the stability is less than a fraction of a degree. Okay, this said, let me come to the core operation. As I said, the cool down started in December. We were able to reach base temperature at the end of January. And so we started the commissioning of the detector from February. What we soon realized is that there was a priority in understanding what was the performance of the system. So we opted for an alternate strategy. So system optimization and science run. So after 2 months of system optimization in order to be able to start with data taking, we had a short science run already mentioned yesterday by Chiara in April, May, then another system optimization during the summer, another science run in August, and now we are again in a system optimization phase. Our aim is to arrive by the next year to the final data taking for science. So go ahead with the data taking. This is a short summary of the already taken data. The data relative to the May, actually, data taking was announced at TAU 2017, while the new ones collected during August are still embargoed, as reminded yesterday, and will be announced on Monday, next Monday, so in a few days. Let me summarize also here some of the characteristics of our data taking. We had 2 short data taking in April, those to which the results so far announced refer, and these are 3 weeks. Let me remind that, as I mentioned before, the number of detectors is about 1,000. Actually, we missed 5 detectors before cooling down the system, so during installation, and after cooling down, we recovered 1 of them, so probably it was a contact with what was recovered during cooling down. But this means that the cool down was really successful since we didn't lose any other detector. Then also concerning the performance, we have still to work on the time devoted to the calibrations. We intend to work on this. And now we were in the initial phase, so we expected to have some trouble or some activities on this phase, but this is the part on which we will work later. As I said before, we are referring only to 3 weeks, which means a total exposure of the order of 38.1 kilogram per year in natural tellurium, and this is already in any case larger than the one collected with 2 years of Quora Zero, the previous experiment. This is the calibration spectrum on the 1,000 detectors, about 1,000. The resolution, I will give the numbers later, is quite good. And let me remind that we are able to see also the low energy lines, because this is another challenge of the experiment. We are deploying the sources directly inside the core of the detector. So you have room temperature sources which are deployed until 10 milli-K, and this was not guaranteed since the beginning. So another challenge which was succeeded. Okay, concerning the resolution, this is the distribution of the resolution on all the detectors, and the harmonic mean of this is about 10.6. This is a factor of 2 with respect to what we expected, but this is also the first measurement. Actually, what we observed in the background is that the resolution is actually better. It was close to 8, and we had worked during the summer in improving. This is mainly related to the noise coming from the pulse tube, and we expect to announce this next Monday. Concerning the background spectrum in the gamma region, also this was already shown. I decided to show just a comparison with the calibration, which is normalized on the thallium line, just to show what is the expected contribution from this line in the ROI. So this is a detail of the ROI, and you see that about 20% is coming still from the thorium series. This is our data shown at TAU, so I will go very quickly on this. This is the ROI after the unblinding, and this is the transition energy. The best fit is negative, and this goes to results which can be summarized in this way. And a background index which is of the order of 10 to the minus 2, but it has to be coped with a 62% efficiency. Now we have worked also on this, and the efficiency is now larger. This was mainly related to the efficiency cut that we decided to adopt for this this initial data taking. The total number of counts is 50, and what we obtained this time was, for those who remember, a discussion concerning the position of the cobalt line in Quora 0. This time the line is centered or is compatible with the nominal value. The limit coming on neutrinoless double beta decay, since I guess you can believe we have no evidence for a peak there, is 4.5 10 to the minus 4, which is larger than the one obtained already with Quora 0. Okay, I can skip this. Concerning a discussion that there was yesterday with Luciano and others, this is what we expect. This is our limit, and this is the median distribution that you expect. We repeated the same also computing on a number of experiments, the limits, and also here the value is compatible with the good with the distribution of limits that you expect from statistical fluctuations. Then we are also combined the results with previous experiments, and what we got is a limit which is now the best, already with 3 weeks, the best limit on tellurium 130. Let me go to some conclusion on Quora. So the science run is continued in August. As I mentioned yesterday, the results will be distributed on Monday. What's next? This is the question. What's next was discussed within a larger group with respect to Quora, and the name is Cupid, Quora upgrade with particle ID. Actually, Cupid will be based on the Quora design, so the fact that Quora design is a success is a good point towards Cupid, and then it will add essentially the need to discriminate between different contribution to the background. And the idea is to use light in addition to heat in order to discriminate the contribution coming from alpha from those coming from beta. Let me try to explain in more detail this. This is what we have now, which is the Quora 0 background model. And as you can see, the region of the double beta decay isotopes is this one, which is dominated by a green line, which is actually the alpha contamination of the supporting structure. So if you are able to get rid of this alpha contamination, of course, you go down by more than ordinary magnitude, and you are able to improve your sensitivity in a very important way. As I can mention that there is not only tellurium in this, tellurium is one of the options. It's not the only one isotope, but I will concentrate on it, of course. So the idea of Cupid is to get rid of the alpha contamination, as I said, by looking at light, because the expected behavior of light with respect to the different particle is different. So the concept is very similar. You separate the different contribution based on the different light response. So the advantages of applying this to tellurium are obvious, and the question is it possible? Tellurium is not scintillating, so the only option is Cherenkov light. Unfortunately, apart from the obvious advantages, there are also issues, and in particular the issues is the low signal coming from Cherenkov light. So you need a very sensitive sensor for the light. And this was the subject of a number of R&Ds that were based on different technologies. And let me say that we have very clear signals of success also at the level of R&D from all of them. And so we are close to make a decision on the technology. Let me just mention quickly the Neganov-Luke. This is somehow technical, is somehow a proportional counter of heat. You are enhancing the heat signal by accelerating the charge carriers, and so you increase the signal. In this way, you can separate, this is one of the examples with the silicon absorber, you can separate the beta signal from the alpha, for which, of course, they are under threshold for Cherenkov light. This is on a larger detector, so more close to the Quora size, and in particular this was also enriched, and also here it was demonstrated that the separation is possible. And more recently, you can look at the references, there was also the demonstration on a real 5 centimeter detector. So let me say that this is a possibility. We have now to go to a demonstrator of the technology. For completeness, I show also other references in this. A very different approach is with the kid. I believe I have no time to enter into the details of this because I have other experiments also to summarize. Let me only say that this is a very different approach. So it's based on a resonant circuit in which the thermal part acts as a varying inductance, and the variation of the inductance is proportional to the number of or to the energy deposited there. This is an implementation of this idea by the Rome group, and these are the first results, which demonstrate that we are close to the resolution which is needed also in this case. Okay, let me now go to another approach, which is SNOPLAS. This is a very different approach. You are loading, you are not using a detector as a source of the decay, but you are implementing the source of the decay inside the detector. This is an old idea, let me say, which is implemented in this case for tellurium. So the questions here are the possibility to load the scintillator with tellurium in a stable and clean way, and of course to realize a system which is able to host this. So most of the work was done in the past years in order to transform the SNO setup in a setup able to host this new goal, and this was, let me say, completed this year. And actually now the status of the experiment is that it is completely filled with water and is taking data on cosmic rays and calibration based on Cherenkov light. And this is a list of all the activities that were done in order to arrive to this point. And now, let me say, this part is completed. The following parts are, of course, the preparation of the scintillators and the loading of the scintillator with tellurium. As I mentioned before, SNOPLAS is hosted at SNO Lab in Sudbury. And concerning the preparation of the scintillator, let me say that also here there was a lot of progress in the past years. Now the system is almost ready, and the commission is ongoing. So I will not enter into the details of the system. It is actually ready to start with the purification and the preparation of the lab scintillator, and the filling is anticipated in later 2017. The last step of the preparation of the experiment is, of course, the tellurium. Tellurium was already procured years ago. It is stored underground at SNO Lab since 2015, but of course you have to prepare the correct mixture in order to load the scintillator. And also here there is progress. The system is not yet completed, but they arrived at a final decision, and the system is being commissioned. The idea, is to implement this in 2018 in order to start with the deployment of the tellurium in 2018. Of course, after the first test with the scintillator. Now the tests are with water. I believe I can go very quickly on the expectation for SNOPLAS because they were announced many times. Let me say that the only point with respect to the past is that they are now pointing to a percentage of deployment which is very close to 0.5% instead of the initial 0.3%. And this is the first phase, which we should start late in 2018, as I announced before. These expectations on the background were shown in many occasions. Let me only point out that the most dominant contribution comes from the 2 neutrino, since the resolution of a scintillator is not so good. Then they intend to go ahead with the second phase, in which they want to put or to bring the loading to 3%. They believe this is possible. There is no actually a demonstration of this, but there will be time during the data taking of the phase 1. A last, if I have a couple of minutes yet, a last experiment or approach that I would like to remind is Cobra. This is a long-standing R&D. This is based on a different technology, which are semiconductors, and the material is cadmium telluride. The advantages of this, in principle, are large. You have two isotopes, which are tellurium and cadmium, and actually the most relevant, the priority of this experiment is cadmium and not tellurium. But tellurium is one of the isotopes, and so I decided to include this in my review. The status, of course, of this development is limited by the properties of the detectors. So far, the detectors are very small. They are of the order of 1 by 1 by 1 centimeters. And this is limiting the total mass that can be achieved, since you need a very large number of detectors. But the technology is working. This has been demonstrated in a run at Gran Sasso with a small size demonstrator, which is 4 by 4 by 4 detectors installed underground. They already published some result, but my message is that they demonstrated that the technique can work both from the point of view of the resolution and of the discrimination. This is actually a step behind with respect to the first approach, which was based on pixelized detectors. So now they do not have a real topological information, but they have in any case an information on the location of the decay, and so they can, let me say, cancel the contribution coming from alpha. So let's see what's going on. They are now preparing a new setup, which will be working at Gran Sasso in the next years. Let me come to my conclusions. So Quora is called and running. This is a technological breakthrough which demonstrates that actually ton-size detectors, bolometer detectors are possible, and will open new ways for the tellurium in the future, and probably not only for tellurium. SNOPLUS also has a large progress with respect to the past years, and actually they are now anticipating the start of the data taking in 2018. As I mentioned, at Cobra is let me say, promising R&D. So far, most of the limitation comes from the dimension, from the size of the detectors. But as usual, we have to support R&Ds if we want to have a future. So my last statement is the interest in tellurium is still strong, and it's making a very promising candidate for the future.
Thank you, Oliviero.